Hello folks, and welcome to the video. This is going to be a short explanation of how the Kerberos protocol works, and I hope that it is going to be understandable and informative without going into too much technical details. And the reason that this video exists is because when I was teaching my own cybersecurity course at the University of Bergen, I could not find a suitable material to show my students, or to use myself. Basically, what was available on the internet at the time, at least, was either too technical, going into low-level implementation details, or it was very general and very abstract, amounting to basically saying, well, Kerberos is a protocol and it provides security by making sure that communications are secure. So I hope we're going to be able to do better with this video, and let's just get started. So let's begin with what Kerberos is and why it is actually needed. According to some sources that you can find, Kerberos can be described as a protocol that allows trusted devices to authenticate themselves to each other over an insecure network. And basically, to get a more concrete idea about what this means, let's imagine that we have a computer network of some sort, which could be the internet or it could be a local area network, for example, and we have a large number of devices connected to this network. Some of the devices are services. So these can be printers, scanners, data storage, servers providing computations, and other things. And some of the other devices are client devices. So these are basically users working on their computers who may want to use some of the services. Now, because the network is insecure, this means that when we send data to a printer, for example, we cannot guarantee that someone else is not going to be able to read the file that we have sent for print. And even worse, a potential attacker might actually edit the document, not allow the document to reach the printer, or possibly send completely fictitious documents for print in a user's name. And in order to prevent all of this, we want to use cryptographic ciphers and other primitives to provide security. Now, a good question would be, why do we actually need Kerberos in the first place? Right? It seems that if we encrypt the data, so if there is a shared symmetric key between each user and each service, then the user can encrypt any data with the key, send it to the service, and then nobody is going to be able to modify the data or to understand what it means unless they're able to break the encryption, which, if we are using a secure cipher, should not be possible. And that's quite true. That's pretty much exactly how it works in Kerberos and in other protocols. And the only issue is that the number of keys that must be maintained and updated is going to be very large. So if we imagine that we have, for example, 100 clients on the network and we have 50 services, then every pair of client and service are going to need their own symmetric key for encryption. If a new device or a new service is added to the network, then new keys need to be created and distributed. If somebody leaves the network or is banned, for example, then keys need to be revoked. And of course, people will occasionally update their passwords and keys, which again requires the administrator to go across multiple devices and update the list of keys. So basically what Kerberos does, mostly, is it solves this problem of key management. Right? It makes it easier to maintain an updated list of users and credentials so that users and services can communicate securely without the hassle of storing hundreds of symmetric keys. Now, before we get to the actual operation of Kerberos, it's probably a good idea to look at some of the main design principles behind the protocol. One of them is that Kerberos is based entirely on symmetric encryption. So we never use any asymmetric primitives like RSA or Diffie-Hellman, for example. Another important design principle is that passwords are never sent across the network. So users obviously have passwords that they can use to authenticate themselves, but the passwords are never going to be sent over the network, and also they're never going to be stored on the client's device. Passwords do need to be stored somewhere in some sort of central repository so that we are able to actually check whether a password is correct or not, but even then they are never going to be stored unencrypted. Another design goal is that passwords are only going to be entered once per session, which provides transparency for the users. A session is basically a period of time where the user is authenticated. So if I have authenticated at 9 a.m., for example, and a session lasts for 1 hour, then I am not going to be asked to enter my password again, regardless of how many or which services I use until it's 10 a.m. And this just makes things more convenient for users of the network. And another important principle is that Kerberos makes it possible for the authentication server, meaning the central unit which provides authentication, to also authenticate itself to the client, so that when you're actually negotiating with this authentication server, you know that you really are talking to the authentication server and not to an imposter. And perhaps a last brief note before we begin discussing the internals of Kerberos. Why is it actually called Kerberos? Now, this is obviously named after the mythical three-headed dog from Greek mythology, which guards the gates to the underworld. But of course the question is why? And surprisingly enough, different sources give different reasons for this. According to some materials that I have found, it is called Kerberos because there are three components in the protocol, which are the clients and the services, and then the central authority, which provides authentication. And each of these kind of corresponds to one of the heads of Cerberus or Kerberos. According to other sources, Kerberos, the protocol that we know today, was actually developed as part of something that was planned to include two other protocols for providing security. So each of these protocols was symbolized by one of the heads of the three-headed dog, and together they were supposed to safeguard all sorts of communication over a network. However, the protocol that we know today as Kerberos was the only one which got implemented and developed, and so today we are left with just this one head. So let's now begin to talk a little bit about how Kerberos actually works. Kerberos is based around a central trusted authority, which is called the Key Distribution Center, or KDC. Now, the Key Distribution Center actually contains some other very important services like the Authentication Server or AS, but we'll get back to that later. Now, the important thing is that information about the users on the network and the services is stored in one place only, which is a database located on the KDC. In this way, it is not necessary for individual devices to keep track of which users are authorized to use the services and who has the right to do what. Services do not need to remember this, and all of this information is stored centrally on the KDC. When somebody wants to use a service, they talk to the KDC, and the KDC will issue a ticket that they can use to show to the service, and in doing so, demonstrate that they really are authorized to use that service. The term ticket is a pretty good analogy, in my opinion, because this is exactly how services in the real world work as well. For example, boarding a plane and flying somewhere is a service, right? And in order to document that we really should be allowed to board a plane, all that we have to do is we have to show a ticket. Employees can verify that this ticket or boarding pass possibly is valid, and then they do not need to manually check that I have really paid for the ticket, that I have really paid for this particular flight, for this particular day, and so forth. If the ticket is valid and the ticket is issued by a central trusted authority, namely the airline company, then the employee knows that all the data in the ticket must be correct and that I am really allowed to use the service. In this case, boarding an airplane. Something very similar happens in Kerberos. When I want to use a service as a client, I am simply going to petition the KDC to issue a ticket. The KDC is going to check in its database that I really am who I say I am, that I really have access to that particular service, and so forth and so forth. And if everything checks out, I am going to get a ticket. I am then going to be able to present this ticket to the service. The service is going to be able to verify that the ticket is legitimate, and then the service doesn't need to know anything more, because the ticket basically says, I, the KDC, authorize this random guy here to use this service, and we're good to go. So how does one actually get a ticket? Well, the KDC contains something called the ticket granting server or ticket granting service, in both cases abbreviated as TGS. So when we want to get a ticket for a printer service, for example, or a data storage service, we have to contact the TGS, the ticket granting service, and say that we want to get a ticket for printing a file, for example. Now, in a weird plot twist, the ticket granting service is also a service. So to use it, we need to already have a ticket. And as you can see, we appear to be heading into some kind of a chicken and egg problem, right? Because in order to use a service, we need a ticket, but in order to get issued a ticket, we need another ticket. So before this becomes too Kafkaesque, we should point out that there is a very special ticket called a ticket granting ticket, or TGT. And this is a ticket that the user is going to receive upon authorization. So when I first log into the network and I successfully authorize myself, so I prove to the KDC that I really am the person that I am saying that I am, I will be issued a ticket granting ticket. And then using this ticket granting ticket, or TGT, I can contact the ticket granting service and I can get issued tickets for other services. So perhaps we should start at the beginning and see how a user can authenticate themselves. So to make the discussion a little bit easier and also to follow the technical specifications of Kerberos, we need to introduce a little bit of terminology, just a little bit. First, a realm is an authentication administrative domain. So basically, when we talk about realms, these are spaces of devices where an authentication server, in other words a KDC, has jurisdiction. So it's possible that in one company we have several local networks, and then each of these networks has its own authentication server. Right? So a realm is basically the set of all the devices, all the services that can be verified by a particular KDC or a particular authentication server. Individual clients and services, and also the authentication server, are identified by something called a principal. So the principal is basically just the name that is used to refer to a client, a host, a service, and so forth. So this is an identifier, right? And the reason that we need this term is because when we are, for example, composing tickets on the KDC side, we're going to include the principal of the client who is asking for a ticket, so that the ticket cannot be substituted for another user's ticket. There are also two types of keys being used in Kerberos, and one of them is called a long-term key. So every client and every service shares a long-term key with the KDC. These keys have to be entered manually into the KDC by a network administrator or some other trusted person. And this is really the only point in Kerberos at which somebody needs to do something manually. The long-term keys are, as the name implies, long-term, so they are not going to be changed every day or every week. It's good cryptographic practice, of course, to change keys regularly, but the long-term key doesn't have to be changed too often. And since this is the only key that needs to be changed if a user joins the network, or if a new service is added to the network, or if somebody leaves the network, this makes key management much easier than otherwise. The other type of key is called a session key. This is a short-term key which is valid for the duration of a session, for example 1 hour, and expires afterwards. When a user authenticates, and authentication, spoiler alert, is going to happen with the long-term key somehow, they will be issued a session key, and this session key can be used to communicate with services. I think we are now ready to begin discussing how authentication and ticket granting actually works. In the first step, a client makes an authentication request to the authentication server. The KDC basically contains two big services or servers. One is the authentication server or AS, and the other is the ticket granting server or TGS. In the first step, when we are authenticating for the first time, we contact the authentication server, of course. And we send an authentication request there. Basically, we are saying, hello, I am a client and I would like to get authenticated, so I can use services in this network. The authentication request is going to contain some information about us. It's going to contain the user's principal. So this is an identifier for me, the client. It's going to contain the principal of the service that we're trying to use, which in this first step is the ticket granting service. It's also going to contain a requested lifetime for the ticket granting ticket. I can say that I would like a ticket granting ticket. In other words, I would like a session which lasts for 5 hours. And it's not guaranteed that I am going to get the full 5 hours, but this is a polite way of asking the KDC to get a 5-hour ticket, for example. And then optionally, I can also provide a list of IP addresses on which the issued ticket granting ticket is going to be valid. So this will typically be the IP of my computer, but I can also specify a set of IP addresses, or I can leave it blank, in which case I am going to essentially be putting a wildcard there, and the ticket can be used from any IP address. It should be noted that the authentication request is sent unencrypted to the KDC. As you can notice, it doesn't really contain any particularly sensitive data, and also we have not really negotiated a session key yet, so we are not in a position to actually encrypt or decrypt anything. At any rate, the KDC, or more specifically the authentication server, or AS, is going to receive our authentication request. And now it's going to start checking some stuff in the database. It has received the principal of the user, in other words, the identifier for the client who is asking for authentication. So the KDC is going to check its database and see whether this user really exists. If not, it's going to send an error message. Otherwise, it's going to create a random session key. So it generates a completely new, random, fresh session key, and this session key is going to be used for communication between the user and the ticket granting service. It also creates the ticket granting ticket, and in the ticket granting ticket it puts the following information. The user's principal. This is because your ticket must have your name on it, right? When you're buying an airline ticket, it must say who you are. It also contains the principal of the service that you're trying to access, which in this case is the TGS. It contains an IP address list, which is the list of addresses that you specified in your request. It contains a timestamp, and this is because it also contains a lifetime. So how long this ticket is going to be valid for. The actual lifetime can be lower than the one that you requested, because it's possible that there is a limit, an upper limit on how long a session can last, and if that limit was 2 hours but you asked for a ticket for 5 hours, then you're still only going to get one for 2 hours. and the ticket also contains the session key. Now, the ticket granting ticket is encrypted with the long-term key of the ticket granting service. So remember that the KDC shares a long-term key with every user and every service on the network, including the TGS. So the ticket granting ticket is now encrypted with the long-term key shared between the KDC and the TGS. This means in particular that the user, upon receiving the ticket, is not going to be able to read it or modify it in any way. So the user cannot, for example, replace the granted lifetime with a longer lifetime, unless they can break the encryption, which of course they shouldn't be able to. The entire reply, which consists of the ticket granting ticket and the session key, is now encrypted using the user's long-term key. So the session key is already a sensitive piece of information, and it must be sent to the user so that they can encrypt and decrypt data when talking with the TGS, right? And because this cannot be sent unencrypted, it is encrypted using the long-term key that the user shares with the KDC. Now, the user receives the ticket granting ticket and the encrypted session key. And it is at this point that the user is actually asked to authenticate themselves. The user is basically asked to enter their password. And the interesting thing is that the user's long-term key is actually derived via a hash function from their password. So the way that this works is that in order to get the long-term key, if one knows the password for that user, one can simply take a hash function, a specific hash function, hash the password, and in this way obtain the key that can be used to decrypt what the user has received. This password, hashed using a hash function, is what the administrator must have set up manually for that user. So every time a new user joins the network, he must most probably go to the administrator's office, type a password on their computer, and then this password gets hashed and stored in the database of the KDC. This hashed password is the long-term key that the user shares with the KDC. Now, however, the user has received some encrypted data from the KDC, and this data is encrypted with this long-term key. The user is now asked to enter their password. If they know the correct password, meaning if they are the legitimate user, then, of course, this correct password gets hashed to the correct long-term key. And then the data that was received from the KDC, which consists of the session key and the ticket granting ticket, can be decrypted. And in this way, the user will get access to the session key. If the user doesn't know the password, then they will not be able to decrypt the data. And that's pretty much how authentication works. Now, assuming that we have a legitimate user who is able to remember their password and has managed to decrypt the data received from the KDC, they are now in possession of a ticket granting ticket and a session key that they can use to talk to the ticket granting service. So now they can make a so-called ticket granting request. So they want to use some particular service, maybe a printer on the network, and now they must make a request to the TGS. And in that request, they must specify which service they want to use. So the user composes a ticket granting request, which basically contains the following information. The principal of the requested service, so which printer or which scanner do I want to use, the requested lifetime for the ticket, so if the request is successful, I will get a ticket that I can use to print, and how long would I like this ticket to be valid for. I'm also going to include a so-called authenticator. The authenticator is something that I use to identify myself, and the authenticator basically consists of the principal of the client, which is me, and a timestamp And all of this is encrypted using the session key that I am using to communicate with the TGS. The timestamp is there to prevent replay attacks, where somebody captures a ticket grant request and then tries to replay it by sending it to the TGS later on in the network. So, back to the ticket granting request. It contains the principal of the requested service, the requested lifetime, the authenticator, and the ticket granting ticket. Since the TGS is essentially a service, in order to use it, I need to present a valid ticket, which is the TGT, the ticket granting ticket that I received from the KDC when I authenticated. Now, the TGS has received my request for a ticket and it's going to process it. First, the TGS, of course, verifies that the principal of the service that I'm trying to access exists in the database. And if it does, if it doesn't, then of course it just generates an error message. But if it does, then it opens, it decrypts the TGT. Why can the TGS decrypt the TGT? Because if you remember, the TGT contained some information which was encrypted with the long-term key that the KDC shares with the ticket granting server. So the ticket granting server has the key which was used to encrypt it. It can now open or decrypt the ticket and it can look at the data inside. It also uses the session key that it shares with the user to decrypt the authenticator. But wait a minute, you might say, where did the TGS get the session key from? Well, if you recall how the TGT was constructed, a copy of the session key was placed inside the ticket granting ticket. So when the KDC, when the authentication server sent the TGT and the encrypted session key back to me, the user, the session key was actually represented twice. One time encrypted with the session key and meant for me, and another time inside the TGT and meant for the ticket granting service. So, since the ticket granting service knows the key that was used to encrypt the TGT and can extract the data from there, it can also extract the session key that we're going to be using with the TGS. Because my authenticator was encrypted with this session key, the TGS can now decrypt the authenticator. And inside the authenticator, it can see the timestamp and it can see the principal of the user. And now, the TGS can check that everything is okay, meaning that the ticket granting ticket has not expired, and this is based on timestamps and lifetimes, that the principal of the service that I'm trying to access matches what is given in the TGT, that the authenticator has not expired, and that the IP address that I am communicating from is contained inside the list of IP addresses specified in the ticket. If all is good, and I should have access to that service, and nothing seems suspicious, then the TGS creates a ticket that I will be able to use to represent myself in front of the printer. The ticket looks very much like the TGT, like the ticket granting ticket, except of course it's meant for a different service. So once again, the TGS generates a random session key that I will be using to communicate with the service. It puts this random session key inside the ticket. The ticket also contains the principal of the client, which is me, the principal of the service, for example, the printer that I'm trying to access, the list of IP addresses where the ticket can be used, a timestamp, a lifetime, which again can be shorter than the requested lifetime, and again, the session key. And all of this is encrypted using the long-term key that the KDC shares with the printer, with the service that I'm trying to access. So you can see that this is exactly the same as when the TGT was generated, right? Except now, instead of targeting the TGS, we are targeting another service. And then a reply is sent back to the user, which is me, and this reply consists of the principal of the service that I'm trying to access, a timestamp, a lifetime, and the session key that was just generated. And all of this is encrypted with the session key that I share with the TGS. And of course, I am also sent the ticket. I cannot open the ticket because I don't know the long-term key that the KDC shares with the printer or with whatever service I'm trying to access, but I can present this ticket to the service. And now finally, it's time for me to actually access the service that I wanted to access in the first place. I compose a request to the service, and now this request is going to depend a little bit on what the service actually is. So if it's a printer, like in this running example that we're doing, then maybe the service is going to contain a file that needs to be printed along with some instructions. Should it be printed in black and white or in color or double-sided or single-sided and so forth. But more importantly, in order to actually document that I really should be able to use this service, I, of course, include the ticket that I received from the TGS. And that ticket was encrypted with the long-term key shared between the service and the TGS, which means that the service can open this ticket, it can decrypt it, and it can look at the data inside. First things first, it can extract the session key that was generated. So now we have a symmetric key, me and the service, that we can use to send secure information to one another. For another thing, it can verify that I really am the person, my principal really does match the principal which was given in the ticket. So basically this works pretty much exactly the same way as when the ticket granting service was verifying my request. Except the only difference is that now the service is not going to issue another ticket for me. Instead, it's going to perform a specific task, and then maybe, possibly, it's going to send me some output back. For example, the document was printed, or if this were a service which was supposed to do some sort of computation or calculation, it would send me the results back. And this is pretty much Kerberos. This is pretty much how it works. We can make a few more comments. For example, as you recall, the long-term key of the user was derived using a hash function from a password. And in fact, this is done using a function called string-to-key. This is not one particular hash function, but rather a slightly more flexible procedure. And the reason that we use this is because Kerberos allows for different encryption methods. The original, the first publicly available version, which is Kerberos version 4, actually only allowed DES, or the data encryption standard, with a 56-bit key to be used for encryption, which is obviously a bad idea. But subsequent updates, like Kerberos version 5, already allowed AES with a much longer key, or triple DES, to be used for more secure encryption. Now, because we can choose different methods of encryption, we can use different symmetric ciphers, this also means that the formats of the keys may be different. So, at the very least, DES or DES uses a 56-bit key, technically a 64-bit key, but 8 of the bits are parity check bits, while AES, for example, can use a 128-bit key. So, this means that we cannot have one hash function which takes a password and gives a long-term key. We should use several different hash functions or several variations of the hash function in order to be able to produce the correct formats. And in practice, this is handled by having this string-to-key function, which receives a password and some information about what kind of key we want to generate, and it's going to generate that key. Finally, Kerberos is the protocol where one of the most famous cyber attacks takes place, which is called the golden ticket attack. We are not going to go into too many details on this, but basically the golden ticket attack is an attack where the hacker or the attacker can forge a ticket granting ticket. And since they are able to forge a ticket granting ticket, this allows them to basically access any service in the network, in the realm which is under the jurisdiction of the corresponding AS. Now, to actually forge such a ticket, one needs to know the hash of the TGS, the ticket granting service. And in order to do that, one needs to already have compromised the KDC. So this is not an attack which is going to allow the hacker to do something he was not able to do before. Because in order to do this thing in the first place, they already need to have full access to the KDC. However, this is called a persistence attack because it allows the attacker to entrench themselves. And essentially, if they have gained access to the KDC, but they suspect that they're going to be kicked out by a vigilant system administrator sooner or later, they can forge a fake ticket which will allow them to go right back in. There is also something called a silver ticket attack, which, as you might suspect, is basically the same thing, except that instead of forging a TGT, the attacker tries to forge a ticket for one of the other services in the network. And basically, one can, of course, take countermeasures. And one of the best countermeasures against both golden and silver ticket attacks is to limit the lifetime of tickets. Traditionally, classically, a golden ticket attack is going to ask for a ticket with a very long lifetime, possibly several years. And there is no legitimate reason why a user would actually ask for a 5-year ticket, right? So if we see something like this, it most probably means that somebody is trying to do something weird. Another nice thing, and actually another important thing to know about Kerberos, is that once issued, tickets cannot be revoked. So tickets can expire, but there is no way to actually revoke a ticket before its lifetime has expired. Which is another reason why tickets should not be issued with overly long lifetimes. Well, I believe that was pretty much it. So I hope you enjoyed the video and I hope this was informative and I hope your understanding of Kerberos is a little bit better now. So, until next time.